Final design project video for Group SR03 at Clemson University. Two-wheeled self-balancing robots are not a novel concept on their own. Both large and small Segway-style robotic models are readily available on the market for uses such as transport or hobbyist tinkering. Our team was tasked with designing and building a medium-scale self-balancing robot. The design was to incorporate Simulink models embedded in a TIVA C-Series Launchpad microprocessor to control the wheel motors based on real-time gyroscope and accelerometer feedback. Our team successfully fabricated a mechanical system using aluminum and steel rods with a pine wood top and base. This also came along with a custom-built power electronics system and an onboard power system. For this project, a series of design specifications were laid out to simulate real-world scenarios. The specifications were as follows. The robot should stand no taller than 18 inches and be no wider than 9 inches. We must utilize a TIVA C microcontroller for real-time control computation. The motors must be powered by team-engineered and constructed power electronics. The use of RC servo motors is also strictly prohibited. A single direct current power source must be used to power the final robot design. And finally, remote control must be implemented in such a way as to allow the robot a full range of motion. This means that the robot should be able to move forwards, backwards, and turn in any direction. One of the major goals of the physical system design was to raise the robot's center of mass. This would conceptually allow for easier balance control. The robot stands approximately 18 inches tall, with wheels approximately 4 inches in diameter. Each wheel is controlled independently using one DC motor per wheel. The aluminum center shaft has a threaded rod running through its center with one platform attached to each end. This design creates both upper and lower level platforms. The top platform holds a TIVA C and Raspberry Pi microcontroller, as well as the MPU 9150 motion sensor chip. The bottom platform holds the battery pack and motor driver circuitry. The electronics of our system include several different types of sensors, 2 microcontrollers, 2 motors, and an H-bridge driver chip. Sensor input from the gyroscope and accelerometer is relayed to the Raspberry Pi. From there, it is recalculated into an accurate angle measurement and then sent to the TIVA C over a high-speed parallel channel. The TIVA then sends a PWM signal and 2 digital logic outputs to the driver chip of each motor. The duty cycle of the PWM output signals is proportional to the speed required for each motor. The digital output pins indicate directional control for each motor, which enables the motors to have bidirectional control. 2 more types of sensors are utilized to send feedback to the control scheme. One is the current sensor, which is included within the driver chip. The second are optical sensors, which are mounted to the bottom platform of the robot close to each wheel. The current sensors measure current in both motor circuits and relay them to the control scheme. The optical sensors are used to track the rotation of each wheel to allow for acceleration compensation inside of the control scheme. Thank you for watching the SR03 team project video. Have a nice day.